Alright, welcome back, ladies and gentlemen. We're moving on to 6.4 day 1. We're talking vectors and dot products. Okay, we just became masters of vectors, and now we're going to introduce something called a dot product. And the dot product is going to allow us to do some other things that we formerly couldn't do, and it's going to make some of the things we did before a little bit easier. So here we go. Alright, the dot product of vectors. Well, first of all, what the heck is it? And okay, we can see right here, basically for vector u, that of course has its x part and its y part. Our book likes to use a u sub 1 and u sub 2 for this, but it's just again the x part and the y part. Same thing with another vector v with its x part and its y part. The dot product, which is going to be denoted this way, the big dot in between the two vectors, hence dot product. Very exciting, I assure you. Alright, anyway, we've got, basically, look, you multiply the x parts, and then you multiply the y parts, and then you add them together. Okay, so let's say if we've got the vector 4, 6, and the vector negative 3, 7, and with the dot product, so I want u dot v, okay, it's just going to be simply the 4, again, the x part, times the other x part, plus the y part, times the other y part. And it's just a matter of crunching the numbers here. So you got a negative 12 plus 42, and assaulting my nearest third grader, they can tell me that that's 30. Okay, so my little red note on the side here. Note that the dot product is a scalar and not a vector. Okay, in case you're not up to your physics lingo, okay, scalar is just another way to say a constant. It's the number by which we are scaling a vector, because typically in vector operations it's something we're multiplying by a vector. So we're scaling it up or down by a constant number, hence the term scalar. Alright, so anyway, there's your vocabulary lesson for the day. Alright, like many mathematical things, the dot products have various properties that apply to them. Alright, so, well, first of which, if I take a dot product, I could change the order, so basically it's commutative. If I multiply a zero vector, and it's probably not very obvious, but the zero vector, that's actually not the number 0, even though it looks a lot like it, because you can only do the dot product between two vectors. So if I have 0, and I'm using that in where a vector should go, it's basically the vector 0, 0. And so that's basically what that is. But hopefully it's no shock if I do something with 2 zeros in it times anything else, I'm going to get 0 as a result. Okay, likewise, the dot product can kind of be distributed. So u dot v plus w becomes u dot v and then u dot w. Okay. We've got this other one that's kind of a distribution-y sort of thing, that if I'm doing a dot product and I want to multiply by a scalar of some sort, I could apply that scalar either after I've done the dot product, I could put it on the first vector and then do the dot product, or I could put it on the second vector and then do the dot product, and it's going to work out either way. And then I have this one here that looks kind of weird. If you do the dot product of a vector and itself, you end up with the magnitude squared. Okay, now that one just looks crazy, at least in my opinion it does, so I'd like to demonstrate that one real quick. But here we go. And I'm just going to arbitrarily pick the vector 5, negative 1. I could have picked anything I liked, but here we go. Okay, so again, let's do v dot v first. Okay, so v dot v is basically 5, negative 1 dot 5, negative 1. Alright, and of course what we do with the dot product, that was just a minute or so ago. You take the x thing times the x thing, and you do the addition with the y thing times the y thing. And that works out to be 25 plus positive 1, so that's a 26. Okay, so I'm now going to do the magnitude squared and see how that works out. Okay, well again, the magnitude of v is again just taking kind of the first half of it squared plus the second half of it squared. Okay, so in this case, it's the square root of 5 squared plus negative 1 squared, and that's going to give us root 26. Okay, but I didn't want to just do the magnitude, I want to do the magnitude squared. So basically what I'm going to do now is put a little square on this guy all the way through. Now be careful when you have the root and all those squares, that might get a little bit messy. If I square everything now, put a little square on this guy, lo and behold, root 26 squared, the root and the square cancel each other out and still give you the 26. Okay, so that actually does make sense. It looks a little bit weird to me, but it actually is a rule that works. And we're going to put it to use here in just a second. Alrighty, the second's up. Okay, now we're going to be using dot products to find magnitude. Okay, now, again, that little property we just mentioned. Okay, if I take the dot product, it's the same thing as the magnitude squared. Well, basically take the square root of both sides of this thing, so then the magnitude, or at least another way of doing the magnitude now, is going to be simply the square root of the dot product of a vector in itself. Alright, now maybe that seems overly whatever, I don't know, but basically, instead of doing the Pythagorean theorem formula, what we can do now here is just go, okay, well, I can do this, I'm just going to do the dot product. Well, again, that's going to be the x thing times the x thing plus the y thing times the y thing. And you might be looking at that going, hey, well, all you're doing is squaring it anyway, and hey, you'd be right. Okay, so I don't think this one's overly groundbreaking, but here you go. You get a 25, you get a 144, which of course adds up to a 169, which everybody knows square roots to be a 13. Okay, so again, I don't think that one's groundbreaking, but the book's going to ask you to do it, so don't freak out when it does. Alright, now here's where the dot product actually has some really nice use, other than what we've seen so far, which I'll admit is not very spectacular. But okay, again, as we get deeper into it, some of this starts making a little more sense, or at least more useful. So here we go. Angles between vectors. Now, to do the angle between two vectors before, if you remember from the last quiz, and I'm sure you do, there was all kinds of crazy law cosine stuff or other SOHCAHTOA things we'd have to piece together. There was a few different ways of doing it, but none of them were very, very smooth. Well, now this condenses it down into one nice formula employing the dot product. Okay, we're going to use a couple of magnitudes on the bottom, we're going to use a dot product on top, and the cosine of whatever that angle is going to equal that. Okay, so just throwing an example down here, if I've got u being 3, 0 and v being 2, 2, let's use this formula. And I picked this one on purpose to say what should it be, because, in case you haven't already thought it, if I just kind of sketch this guy out real quickly, 3, 3 would be going about right here. Let's just call that about 3 up to that point. So 1, 2, 3. Okay, so there's my vector u at 3, 0, and my vector v is at 2, 2. That goes over 2 up 2, and hopefully I'm not challenging anybody here by saying that that's going to be a 45-degree angle. So it should be a 45-degree angle between these two vectors. Okay, so let's put the formula to the test and make sure that it actually works. Alright, so the first thing I'm going to do, because I need to know the magnitudes, is calculate them really quickly. Okay, and again, we could do that dot product thing that we just did a second ago, but I'll be honest, I primarily use the normal one that we've known and just kind of do the Pythagorean theorem on it. So here we go. Alright, magnitude of u, okay, is just square root of 3 squared plus 0 squared, and hopefully I'm not shocking anybody to tell you that's 3. And then same basic thing, magnitude of v is just going to be the square root of 2 squared plus 2 squared, which is square root of 8, or better yet, that's going to be simply 2 root 2. Alright, so I've got my two magnitudes, and I can do my dot product if I wanted to, and let's just include that as part of the formula. So here we go. So the cosine of theta is going to be, again, dot product. So I'm going to take the x part times the x part plus the y part times the y part. Alright, and again I'm going to do the product of my magnitudes on the bottom, so I've got 3 times 2 root 2. Alright, on the top I've got a 6, and on the bottom I've got 6 root 2. Okay, so let's just pretend for a second that you don't look at that and think, oh, the 6's cancel and it's 1 over root 2, and then that rationalizes to root 2 over 2. Let's just pretend for a moment. Okay, and basically we can type that in the calculator and get some equidecimal. Alright, so we get what we get, which is the equidecimal of 0.7071 dot 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 dot. Equidecimals forever. Okay, so again, let's pretend we don't recognize what that actually is. Alright, so basically condensing what I have right here, I've got cosine theta equals that equidecimal. And then so of course to get theta, I go inverse cosine of that equidecimal. And certainly, after a few button pushes, I do get that 45 degrees that I was kind of expecting at this point. But basically that's how that works. And again, instead of doing a big nasty law of cosine sort of thing, that dot product enables us to do this in a much, much nicer sort of way. Alright, but what would happen if your vectors were much, much messier looking? Oh my gosh, look at those things. Okay, well, one thing to take note of first is that the angle measures in both of these are the same, at least within its own vector. So u has got pi over 4 for both, and then v has got a 3 pi over 2 for both. Also notice that it's cosine first and then sine later. In our next section, we're going to be employing some notation that looks very similar to that, so basically we're just prepping it for you now. Okay, so anyway, well, first thing first, cosine pi over 4, let's clean that up. Okay, being the masters of trig that we are, Okay, if I have pi over 4, it's looking right there, and now the cosine of pi over 4 is simply going to be root 2 over 2. Likewise, sine of pi over 4 is also root 2 over 2. Okay, so basically what I can do is turn my u into something a little more user-friendly. Root 2 over 2i plus root 2 over 2j. Okay, that's a little nicer looking. I can do something similar with v. Okay, I'll circle over here this time. Well, 3 pi over 2, again, is basically straight down. So, remember, and so then the cosine, remember, is my x-coordinate, so this would be a 0 for cosine, and then my sine would be the y-coordinate, which is -1. Okay, remember, that's 0, -1 right there. Okay, so again, turning v into something a little more pleasant to look at. Cosine of 3 pi over 2, again, is a 0, so this is really 0i, which, of course, you could leave off if you wanted to. And then sine of 3 pi over 2 is really a -1, so I probably didn't need that plus sign, but there it is anyway. -j, okay, that's bothering me, so I'm going to clean it up. Okay, I feel better. Alright, so at this point, again, what we're trying to do is find the the angle between the vectors. So again, first thing I need to do is figure out my magnitudes, and then I'll use those in my formula. So again, magnitude of u, well, again, hopefully we can remember enough trig to know that since these are 2 unit circle values, and since we're in a unit circle, that means my hypotenuse is 1, which is effectively the magnitude here. So magnitude of u is 1. That's a very nice number to have. Likewise, the magnitude of v, well, if I'm going 0 minus 1, basically, alright, my magnitude of v is also a 1. Alright, that being said, okay, I've got cosine of theta equals, okay, again, I need to do the dot product, so that's root 2 over 2 times 0 plus root 2 over 2 times -1, and that's going to be all over in the product of my magnitudes, which is a pretty simple 1 times 1 in this case. Alright, so I'll just work it straight across for a second here. The root 2 over 2 times 0, of course, cancels out, and then this guy ends up being a negative root 2 over 2. Alright, and again, I've got a 1 on the bottom, so I'm going to leave that off. So basically what we've got here is cosine theta equals a fairly nice root 2 over 2. Again, fairly nice, assuming that you remember your trig values. Alright, so basically, again, theta is going to be the inverse cosine of negative root 2 over 2. And one of those things that, you know what, this problem started out using radians, so let's make sure we finish it in radians. So our theta, our angle between the vectors. Alright, again, if you remember the cosine of negative root 2 over 2, going back to our unit circle, inverse cosine lives in the first 2 quadrants. So if I do the inverse of negative root 2 over 2 for cosine, it lands me right there, which is, again, a 3 pi over 4. Okay, hopefully you haven't forgotten too much of that stuff at this point. Alright, let's take a look at another scenario where this dot product cosine formula can kind of come in handy, and it's if we want to know if the measure of the angles of triangles for whatever reason. Alright, so again, if and this is especially good if you've got this thing superimposed on a graph, or at least you have a situation where you can kind of superimpose it onto a graph. Sometimes you can do that based on the information you have, but anyway, here we go. Okay, let's pretend that A is at 3, -2, so right there I've got A, B is going to be 4, 5, there's my B over there, and then C is being -1, 3. Right about there is C. Okay, so I'll do my best to draw a reasonable triangle through these 3, just so we have some kind of ballpark frame of reference to shoot from. Okay, let's pretend that actually hit there. Alright, so again, I want to find all the measures. Well, realistically though, keep in mind that as soon as I find 2 of them, the third one is simple. Just do 180 minus the ones you've found already. So you don't have to do what I'm about to do 3 times, you can get away with just doing it twice. Okay, well, just for argument's sake, let's find angle A. It's the one I drew the worst, why not? Alright, so for angle A, okay, the 2 vectors that form angle A basically are angle AB, and angle, vector AB and vector AC. Okay, so basically just imagine the sides of the triangles being vectors. Alright, that being said, okay, in order to use that formula we were just talking about, we need to know what the vectors are in their component forms and their magnitudes, and then we can use our formula. So here we go. Alright, vector AB is, okay, again, if we look at A to B, again, maybe it's handier to have our coordinates listed next to the points. 5 and -1, 3. Okay, now again, the easiest way to do this is just look at the x-coordinates. From A to B, I go from 3 to 4. Well, that's an addition of 1, basically. And from -2 up to 5, that's an addition of 7. So vector AB's component form is simply a 1, 7, and then from there, calculating its magnitude isn't too tough. Again, just play Pythagoras on this guy, and I got 1 plus 49, so I've got root 50. Okay, now you may be tempted to turn that into a 5 root 2, but really this isn't a number that's going to be a final answer. This is just something I'm going to plug into a formula, so you could do that, but it's not really important for what we're about to do. Okay, that being said, we also need AC. Okay, and from A to C in the x's, I go from 3 to negative 1, so that's basically backing up 4. And then from negative 2 to 3, that's going up 5. Alright. Okay, again, getting our, whoops, that's a C. Okay, you don't realize that I messed up. Okay, since that's AC, again, 16 plus 25 is 41. Alright, again, that one wouldn't simplify no matter what you wanted to do. Alright, so anyway, there's all the information we need. So then, cosine of theta equals, again, our dot product, so 1 times negative 4 plus 7 times 5 is our numerator, and our denominator becomes, again, the product of the magnitudes, so root 50 times root 41. Okay, again, that's why I didn't worry about simplifying, because I knew I was just going to plug it in and do some other stuff with it. Okay, plugging this mess into my calculator, or doing whatever I need to do, eventually gets me to actually 31 over root 2050, which is kind of messy, but getting that typed into my calculator, turning that into a decimal, and then basically what I need to do from there is inverse cosine that icky decimal, which in this case works out to be 0.6846, and going on forever. So that gives me angle A. I guess I should use an A right there. Angle A equals 46.789, so I'm just going to round that to 46.8 degrees. Alright, so there's angle A. Again, I could just simply repeat that process to do either angle B or angle C, although just as you do that, keep in mind that when I figured out vector AB, okay, I can't use that same vector if I'm finding angle B, because now that's vector BA, and vector BA would be a negative 1, negative 7. So you have to kind of reevaluate your vectors for the other angle that you're going to do, so don't fall into that trap. Other than that, hopefully that made a little bit of sense. I apologize for the theta versus A thing right there. But if you have any questions, obviously grab me as per usual, and I'll see you in class.